I will just quickly introduce myself. My name is ANOVA Chatterjee and I am taking this Biostatistics and R class. And this week we are going to deal with the different types of tests that we can use to compare means between various samples. Does anyone have any questions from the previous weekend, like the previous classes they want to ask? Okay, if not, then we can start today. So I hope everyone has their R studio up and running. The first thing we will do is that we will refer to a PowerPoint right here. So if in the last class, just a quick reminder what we did, we looked at different statistical analysis and how to make a hypothesis and figure out different parameters that are involved in it. Especially the ones we want to deal with are the p-value. The p-values are essentially the descriptive values which gives us if two different data sets are similar or different from each other. So if the p-value is less than 5%, so 0.05, then we will say that two different distributions are different. So today we will learn on how exactly to use that information using different type of tests that you can run. So this entire chart is something that you should refer to and probably is the most important piece of data that you will see in the entire course on which test to use in which scenario. So say you wanted to, so this is a pretty simple straightforward flowchart kind of a thing. So what type of data that you are dealing with, if it is continuous or categorical data is one where you have different names to the data or different tiers to the data that you want to compare. Say when you toss a coin, if it is coming heads or tails, how many times are they coming. So heads or tails are two different values, so it is a categorical data set. Even when you are rolling a dice, you have only 6 options, 1 to 6. So how many times like are you throwing a 6? So that is a categorical data set where you have separate discrete values and the frequency or the number of times the values occur. So if you want to test if say your dice that you were rolling is fair or not, then obviously a fair dice should have a probability of 1 by 6 for each of the faces coming up. If you want to compare the dice that a very shady person has given you and see if it actually matches up to the fair dice that you have, you will compare the distributions using a chi-square test. Similarly, if you have a continuous data set in which you have number of different variables, say the marks that you have gotten in the last test, so that is a continuous data set where you have a number of different continuous values that can occur and you wanted to compare between them. Like say you got some marks in mathematics or compared to some marks in biochemistry and you want to figure out which you are better at. So that is a continuous type of data that you want to compare. Next would be what kind of question are you asking? The question could be a difference kind of a question. So what is the difference between the marks that you got in mathematics versus biochemistry? And then you go ahead and go down this flowchart and ask how many groups do you want to compare? Do you want to compare two? So in our example, you wanted to compare the marks between mathematics and biochemistry. So you have two groups that you want to compare, followed by if it is a parametric data set, are you going to compare a small part of your entire exam, or say you wanted to compare the entire batches results. So is it a population data set or a parametric? If it is a parametric data set, you use a t-test. If it is not, then you use a Wilcoxon test. If there are more than two data sets that you want to compare, say you wanted to compare 3 or 4 subjects, then you have to again ask if it is a parametric data set. If it is, you use ANOVA. If it is not, you use some other test. So most of the time we are going to deal with parametric data. So most of the time we are going to deal with t-tests or ANOVA, both of which we are going to cover today, as well as chi-square. The other type is you want to find a relationship between your two data sets. Say there was a teacher A that was teaching you mathematics, teacher B who was also teaching you mathematics, and they'd have different papers, and you want to figure out is depending the teacher A teaching you better compared to teacher B. So you want to find a relationship between the teaching style and the marks that you got. In that case, you have to ask an important question, which is, do you have a dependent variable? So in our example, it actually, the grades or the scores that you got is dependent on either teacher A or teacher B. So you have a dependent variable. In that case, you do something called regression. You actually figure it out if there is a relation between the teachers and the marks. So you do a regression. If there is no dependent variable, if you are dealing with two independent ones, then you use the Spearman test or the Pearson test. This part we will be dealing in tomorrow's class. So categorical tests, you use chi-square. If you are comparing two means between continuous data, you use t-test. If there are more than two, then you use ANOVA. It is as simple as that. Is that okay? Does anyone have question from this?
Sir, I have a question.
Yes, please go ahead.
Sir, does this parametric data does it mean like a group of data, and is it always more than two, or like is there a specific number to denote a parametric data?
Oh, you want to know if what parametric means. So when I mean two or more groups, I actually mean that how many datas are you comparing. So mathematics versus biochemistry, or mathematics, biochemistry, molecular biology, and three or four. That is when I mean groups. So that doesn't depend on if the data is parametric or not. What parametric data essentially means is that uh, say remember in the first classes we were discussing that when you are dealing with population, you do not actually cannot actually take the entire population into account and deal with everything at once. You take a small sample out of it. So when you take a small sample out of it, whatever information you get out of the sample is known as the estimate or the statistic, whereas the entire population data is known as the parameter. So say your entire batch was giving an exam for mathematics, and you had like 40-50 people in the entire batch, and you figure out the mean for the marks of everyone. So that is a parameter data. The entire population you are taking into account and figuring out, yes, this is the mean of the entire class. But say you cannot go ahead and ask 40 people what is the marks that you got, so you only took a sample, 10 people, and you figured out the mean of just the 10 people. So that is a statistic. So parameter is when you have the entire population in your hand and you know every one of the marks of every one of the individuals. That is a parameter data, the population data. When you are dealing with just a small amount of people, only the sample of 5 or 10 compared to 100 or 40, whatever your entire population is, that is a statistic or an estimate. So in case you are dealing with a statistic or estimate, or the smaller sample that you have taken, you go down the left wing of this. If you have the entire data of the entire population, you now go down the right wing of this. So you deal with parameter data using ANOVA. If you don't have parameter data, then you like only a sample, small amount, then you use this test. Is that okay?
Yes, sir. And sir, another question: what is the meaning of regression and correlation?
So regression, which we will deal in the next class, regression is when you try to figure out if there is relationship between two different variable. So say if you wanted to plot the marks or you got in mathematics versus the marks you got in biochemistry, and figure out if there is a relationship between the two. Say you are very good at biochemistry and not very good at maths. Is that actually something that happens all over the population, that everyone that is good at biochemistry is not actually good at mathematics? So that kind of a thing you do using correlation. You figure out the relation between the two. Regression is a bit different. Regression is when you know that there is a dependent variable and a independent variable. Say your marks in mathematics are the dependent variable which depend on how much you have been practicing. So the relation between how much you are practicing versus how much marks you got, you use regression to figure that out. Both of these actually look like a scatter plot on a graph, and then you draw a line, and the slope of the line determines if they are related or not. So we can discuss this like in the next class. I will be able to better explain the entire relation between correlation and regression. Like when I show you the data as well as the graphs, I think that will be more clear. Is that fine?
Yes.
Okay. So I would like everyone to go right off to our studio and start. uh, our studio, you can open our notebook, and we are going to write some code and figure stuff out. So I will share with this notebook with you, but for the while I feel that if you start coding yourself, you will be able to better understand everything. The first thing you should do is uh, run the libraries tidyverse and dplyr. Everyone please go do that. Don't have to write this. This is just the image that I just showed you. It is embedded in the R notebook. You will get it when I share it with you. Just this two should work for now. Let me know if you are done with this. Has everyone done this? Yes, no's, please.
Yes.
There seems to be a conflict in for me for some reason.
There seems to be a conflict. Where is the conflict?
Yes, I'm checking that.
You just.
So library tidyverse,
Haha.
library tidyverse, it shows, it just says use the conflicted package to force all conflicts to become errors. Uh, can I paste the message to you in the chat?
You can share your screen and show me. That will be easier.
Okay, so just a sec.
Yeah.
1 second, sir. Sir, is it visible?
Not yet. It will come up. Yes. Okay. Okay. Just
Sir,
go scroll
this is what I'm
scroll
getting.
up a bit. In the R notebook, scroll up. Okay, so you are doing it in the same R notebook, right? So you are essentially you had previously installed library tidyverse, and you are doing it again. That is why it is showing an error. It should not
Oh, okay,
stop
okay.
you
So,
from doing anything.
okay, sir, it's not an error then.
It is not an error. Just is showing that.
Okay, okay, thank you, sir.
Okay. So the first test we are going to deal with, so I will show you this again. So the first kind of thing we are going to do is look at when you want to compare two different data sets, just two different data sets of continuous variables. So what type of data? You have continuous data, you want to figure out the difference between two datas. How many groups you have? We have two, and we are going to deal with parameter data only, so we are going to do a t-test first. Okay, so what is a t-test? So for this we are using the empty cars data set that we have been using. So I think everyone is familiar with this. It is just a bunch of cars, and what is exactly the different characteristics of the cars using the mileage, the number of cylinders they have, displacement, HP, and everything. So we are going to use this data set only. The first thing that we want to do is that, say you have we know that number of cylinders the car has, it is probably the more powerful the car is. So you have probably would have heard that there are V8 engines, V12 engines, which are super powerful cars that go at very fast speeds. So say you wanted to figure out, in this data set you have only three types of engines and cars, which is a 4 cylinder, a 6 cylinder, and a 8 cylinder. So if you wanted to figure out if, say, the 6 cylinder, how does the HP or the horsepower of the 6 cylinder engine compared to all the other cars in the entire data set? So is a 6 cylinder car stronger than the average car that is out there, or no? Is the question that you wanted to ask. So you are comparing a statistic of a particular group, which is a 6 cylinder car, to the entire population. In that case, you use something called a one sample t-test. So you wanted to compare a particular parameter between a small group compared to the entire population. For example, say you wanted, so all of us have done the Mathematics 101 course in the first year of our BTechs. So if you wanted to compare how does the biotechnology people do in Mathematics 101 compared to the entire college. So you have a small population comparing their average to the entire large population of the entire college. So small group comparing to large, but you're comparing the same thing. In that case, you use a one sample t-test. Here we are comparing the horsepower of the 6 cylinder versus all the cars out there in the empty cars dataset. So one sample t-test is there a difference between a group and a population? To run the t-test, we will first have to load a library called LSR. So library LSR, and the t-test function only takes factors. So factors, if you remember the last, I think the second last class that we did, factors are variables which have essentially categorical data. So you cannot do maths with them, so you can't add two factors together. They essentially are like head and tails. So first thing we will do is that change the cylinder column of empty cars to a factor. So you just put this in. We have used this only, right? Yeah. So you just put this in. 6 cylinder, we will mutate the entire empty cars dataset, filter for only 6 cylinder cars, and fix the cylinders as a factor. We have done all of this in the last class, but if anyone has any problems you can ask, but for now you can just write this down. So with the filter command, we are only choosing cars with 6 cylinders, and with the mutate command we are changing the cylinder column into a factor. You can even print 6 cylinders out like this, uh, to see if it works. So it works. The 6 cylinders, only cars with 6 cylinders have come up in this particular data set, and they are now a factor. You see, FCTR. Everyone on this? Okay, Shreya. Nice. So, has everyone done this? You have been able to make a six-cylinder data set? You can put up a thumbs up if you have been able to do this.
Yes, sir.
Okay. Now, so we are going to use the library LSR. So type this in library LSR, and we are using the one sample t-test. So for actually not the one sample t-test, we will first do just the t-test. For the t-test, the command is t-test followed by what you want to like what is the mean of the data you want to compare. So I want to compare the HPs of the six cylinder cars, and what you want to compare it to the mean of. So here we are only comparing the mean. So whenever you are talking about comparing data sets, most of the times you are just comparing the means of the data sets. So mu is the population mean. The population is empty cars and the HP of the empty cars, the entire population of empty cars. So I have figured out the mean of the HP of the entire empty cars and stored it in mean HP, and then we run the t-test x equal to six cylinder HP and comparing it to the mean of the HP of the entire empty cars dataset. So please let me know what you see. So it would be very nice if someone displays their screen and shows what they see, like, or otherwise you can see what the test will look like on my screen as well. Let me know if everyone has run it. It should look something like this. Everyone done with this? You can put a thumbs up if you have.
Yes, sir. Yes, yes, sir.
Okay. So let us go through what exactly we are looking at here. So this is a one sample t-test. One sample t-test is when you are comparing small group with the population. So here the important thing that you look at, as I've said before, is the p-value. If the p-value is significant or not. So here we have a p-value of less than 0.05. So obviously the p-value is significant. So our t-test only asks the question if our mean, the true mean is the mean of our six cylinder HP, is equal to the global mean or not. So it has answered that true mean is not equal to the global mean that we have seen. So that's very nice. And it has also given us the mean that we are talking about. So this is the mean of HP of all the six cylinder cars as compared to the mean of HP of all the empty cars data set. So obviously they are different, and with the significant p-value you can say they are significantly different. So the six cylinder mean is different from the global mean, which is something which is very nice. But the question is now, is the mean greater or lesser than the empty cars global mean? So is the mean of six cylinder HP greater or lesser than the mean of the empty cars dataset HP? For that you will have to run the one sample t-test which looks very same to the t-test, but here there is one extra parameter called one-sided. So this parameter will either take greater or less in its quotes, and if you run this, it will actually tell you that the population mean is less than the mean of the mean of the six cylinder cars is less than that of the population mean. So our six cylinder cars are actually less powerful than the mean of the all the cars that we are looking at. So here we have one sample t-test. The data variable is 6 cylinder HP. The mean and each standard deviations are given. The null hypothesis is that population mean is greater or equal to the empty cars dataset. Alternate is it is less than the empty cars dataset. And we have a significant p-value here, which shows that our six cylinder cars are losing against the empty cars dataset. Is that okay? Did everyone get it? So this is how we read it. So you have the mean here, the alternate hypothesis, because we have put in less here, which means alternate hypothesis is that our six cylinder cars are less powerful than the empty cars, and the p-value is actually significant, which means that yes, the alternate hypothesis is correct, that our six cylinder cars are less powerful than the empty cars dataset, and so we accept the alternate hypothesis that the population mean is less than whatever the mean of the empty cars dataset is. Yes, Nandini, go ahead.
Sir, I'm a bit stuck. The muted function is not working in my console.
Muted function is not working. Okay. Can you share your screen and show it to me?
Is it visible?
Yes, it is visible. Could not find the function muted. Have you run the dplyr library?
Yes, here.
Hmm. You do one thing. Install packages tidyverse, you remove.
Okay.
Now run. Now run the one that you have that you were showing that muted is not working. Yes, let me. Okay. Now quickly go and
Okay.
run all the ones that I showed you. The t-test. Quickly run the t-test. I hope my screen is visible again or no. Is my screen visible? Yes, my screen is visible. Yeah, this is the one that we are talking about. One sample t-test. If you run with the six cylinder cars, comparing them to the mean of empty cars, then you figure out that the p-value is actually significant. So the mean of those six cylinder cars are actually less powerful than the empty cars dataset. Does everyone agree to this?
স্যার টি টেস্টটা আরেকবার বল
So t-test is comparing the mean of a sample that you are looking at compared to the mean of the entire population. Here, the data that we are looking at is the horsepower of only the six cylinder cars and comparing it to the horsepower of the entire population, which is the empty cars dataset. When we run the t-test and put in less as a one-sided parameter as less, then the t-test tries to figure out if our 6-cylinder cars, the HP of the 6-cylinder cars, are less than the HP of the entire population. So here it is shown right here as the alternate hypothesis. The mean that we are calculating, which is the so here it is written as population. The population here is only the 6-cylinder cars. So the HP of the 6-cylinder cars is less than the HP of the empty cars dataset, which is 146.6875. When we run this test, we find that the p-value is 0.019, which is less than 0.05. So the statistic is significant. So our 6-cylinder cars, the horsepower of 6-cylinder cars is less than that of the horsepower of the entire population empty cars dataset. This is what the test shows us. Is that fine?
Yes, sir.
Okay. Rupkatha?
Yes, sir. I am stuck in my console. It is showing that the one sample t-test function could not be found.
Have you run the library LSR?
Yes, sir.
Have you checked that the spelling is correct?
Yes, sir. I've checked everything.
Okay. But देखो नहीं screen to share करे?
Okay.
Run.
Okay, I think I got it now.
Okay.
Okay. Sorry, sir.
No problem. Okay, so what I will do is quickly I will make another meeting because it seems today again we have a time limit of 1 hour only. So I have made another meeting. I will share this in the chat. Make sure that everyone you know logs in when this meeting is about to end into the new one. So I believe my screen is again visible. Huh. So everyone agrees with this, right? That the t-test is showing that our mean of the 6 cylinders population is less than that of the population mean. Anyone has any questions regarding this? Okay. So this test is especially powerful when you're dealing with two samples, or like one sample t-test is especially powerful when you're dealing with a small sample and you're trying to figure out where it lies as compared to the entire population. As I said, you wanted to figure out if the marks that you have getting in mathematics in biotechnology department is less than or more than as compared to the entire college. So this is the test that you will use. Or if you want to look at a scientific example, so say you were trying to figure out, you were treating your cells, bacterial cells, with a particular drug which prevents them from dividing. So if you wanted to figure out the doubling time of the cells that you are working with as compared to all the cells out there, which value you will have to have beforehand, then you can also use the one sample t-test. So there is also one something called a two sample t-test, in which the answer, so that is the t-test that we ran before, in which you actually figured out if your group mean is different than your population mean. That is the only thing that you will be figuring out with it. But using the one sample t-test, you will be able to figure out if it is less than or more than the population mean. So if they are different, you use the t-test. If you actually care if they are less or more, then you use the one sample t-test. Very good. So we backed up the 6-cylinder cars, and it seems they actually have less HP than the entire population. But why would that be? One reason that could be is that there are also 8-cylinder cars in the empty cars dataset. Maybe the 8-cylinder cars are beating the 6-cylinder cars so badly that the population mean is actually much more than the 6-cylinder mean. So now we can actually try and figure out if this is the correct hypothesis, that the 8-cylinder cars, they have so much more HP than the 6-cylinder cars. So in this case, you are comparing two different groups. If you want to compare two different groups, you use the independent t-test. So to use the independent t-test, the first thing that you will have to do is that you have to take the two groups and make one table out of them. So first we do is that we filter the empty cars dataset and only take the two groups that we care about, the 6-cylinder group and the 8-cylinder group. And then we mutate this particular dataset to set the cylinder as factor, because as I said, the t-test only takes factor variables. So first we filtered and only took the groups that we want to compare, the 6-cylinder and the 8-cylinder people, and then we made the entire cylinders data into a factor, because that is the only thing that our t-test can take. So run this particular part of it, and you should be able to see that you have a new data set where the cylinder is set as factor, and you have only 6 and 8 cylinders in the entire data set.
স্যার একটু কোড দেখান না
কোডটা দেখাবো, এই যে
স্যার এই কোডে অ্যাজ ডট ফ্যাক্টরটার কি কাজ আছে
said that the t-test, so factor variables are essentially just, you can treat them as names that correspond to particular values. So similar to heads and tails, and number of times heads and tails occurs. Similarly, what is the value for 6-cylinder, and what are the different parameters associated with 6-cylinder engines? So factor is just that, you just convert the variable which is ordinarily an integer to a name kind of a thing, which is a factor. We do this because the t-test function can only take factors as their particular inputs. So we have to run this. It does not do anything with, it is not related to the t-test itself, but the function that we are using in R.
ওকে
I think ওটা হয়ে গেছে হবে. So next what we do is that we run the independent t-test. So the syntax is, you write independent t-test, and you first have to do put in a formula. The formula actually puts in that the particular thing that you want to compare between two groups and the two groups. So here we want to compare the horsepower and the groups that we want to compare it between are the cylinders. So we write HP, this squiggly line, which you can find on your laptop, I think towards the left side, and then cylinders, followed by which data set they are coming from. It is coming from the SECYL data set, and then the variance equal to true. This we will see what this is later on. So if you just run this, you will be able to see the entire you will be able to see the t-test running. So here we have the student sample t-test. The outcome variable is HP, the grouping variable is cylinder. So this is what you're comparing, this is what you're comparing between. So here they have given a description of it. So 6 cylinder have a mean horsepower of 122, 8 cylinders have essentially double at 210. So the question that was asked is the mean different between the two groups, and the p-value is greatly less than 0.001, so hugely significant. So you definitely can agree to the alternate hypothesis with the different that the population mean differs between the two groups. So essentially the alternate hypothesis is different population means in each group, so the means are different and the p-value is very 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 significant. So you can definitely agree that the 6 cylinder people and the 8 cylinder people have very different HPs, and from this value you can actually figure out that the 8 cylinder leave the 6 cylinder guys in the dust way 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 behind. Does everyone agree to this?
Yes, sir.
Sir, এখানে last লাইনটা that is where dot equals to true, ওটার মিনিংটা কি, লাইক ওটা কেন লেখা হচ্ছে?
So one other thing that before going to that is there is something called this everything else I think we have covered. This is something that we had just touched upon, the estimated effect size, the Cohen's d. So what this means is that the p-value gives you statistical significance. Very good. So they are significant, statistically significantly different, but are they practically different? So say you were comparing marks between you and another person A and B, and statistically both of them are getting different marks. One is getting a 95, other is getting a 98, and you have a good p-value, you say yes, statistically significant. But do you actually care if you get a 98 or a 95? It is still hugely greater than anything else anyone else is getting. So the practical aspect of the difference between the two data sets, that is what is given by the Cohen's d. If this value is greater than 0.8, then you have a practical difference between the two parameters that you are comparing. So here you have a value 1.962 that is hugely greater than 0.8. So you say that yes, the HP is actually practically also significant. It is not just it is that the p-value is significant, the actual effect size is also significantly different. So now the next thing is the variance equal to true. So most of the tests that we are going to do today assume that the variance between the two samples is the same. So say that if you actually plot, so you remember what variance is. Variance is essentially how different the entire data set is, not how different, how further the data distribution is spread. So variance is essentially how far away that all the data points are from the mean of the distribution. When you say variance equal to true, you say that the two data sets that you are comparing, the 6 cylinder one and the 8 cylinder one, both have similar variances or equal variances. Where will it make a problem? So say that in the 8 cylinder data set, only 5 cars were who had 1000 HP and rest of them had 100, and that is why the average comes out to 209. Whereas in the 6 cylinder one, there is no such case. Everyone is actually pretty evenly spread out around 122. So the variance is different. So in that case, if you go ahead and compare, then you might not get a very good result, because in one data set only, because because of some outliers, the entire dataset is skewed towards one mean, which is actually not the true mean of the dataset. So if the variance between the two datasets are not equal, then you cannot use the t-tests. So what will you do in that case? You will have to first figure out if the variance is actually equal between the two datasets or not. For that, you use the leave-in test, the Levin test, whatever. This idea is the same, that you just compare the variances and see if they are actually very different from each other. So to run that, you use the library dissect tools, and leave-in test has a similar idea to this. You put in a formula, this is what you want to compare, this is what you're comparing against, these are the two groups, and the data is ACCYL. When you run this, you see that the p-value, so this is the leave-in test for homogeneity of variance, this, and here the value that you want to look at is PR or greater than F, this value. If this is essentially the p-value for leave-in test, if it is less than 0.05, then the variance is actually different, and in that case you will have to use the Welch test, which here is very easy. You just put this to false. If you put this to false, you will get the Welch test instead of the t-test, and then the calculation will be the same. You just look at the p-value and the means, and you figure out what you want to figure out. But essentially, for any kind of data set that you are comparing, first thing you should do is do a leave-in test to figure out if the variance is the same. Most of the time it is the same, so we are not doing it for all the examples we are dealing with here. But essentially this is what you have to do. If you guess that the variance is not equal between the two tests or two data sets, you run the leave-in test, figure out if they are actually different from the p-value. If they are not different, then the variance is actually equal, and you can run the t-test as is. If it is oh, 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 open. I have sent the Google Meet link in the group. Please send it to others and ask them to join fast, because this meeting will also end in 1 hour. Okay, coming back. I don't want to do that. So as we were talking about, before using any test, the first thing you should do is that run a live-in test, and that will tell you if the variance is different. If the variance is different, you don't put variance equal to true. You to put it as false. And if it is actually not different, you put variance equal to true, and that will run the normal independent sample t-test. So what did we get from this? We got that the yes, Nandini.
Sir, I have run this code, but it shows that there is no package desk tools.
হ্যাঁ স্যার আমারও দেখাচ্ছে না।
হ্যাঁ সত্যি ওকে কেন আমার তো এমনি কিছু হচ্ছে না। Are you putting in the spelling correctly?
Yes, spellings are correct.
Okay, let me run. What happened? না তো ধীরে ধীরে চলে গেল। Is there some package installation that I have missed here? So the first thing you do when you figure something like that out, you ask the help part of it. Does to you can try installing, I think, the desk tools package. Install package. I think if you do this, it will work. Just install the desk tool packages first. Mine is already installed. I think you can try doing that and it should work. Is it working?
Yes.
Okay. So yeah, so we have actually statistically shown that our 8-cylinder car dataset has a hugely greater HP or horsepower compared to the 6-cylinder car's dataset. So that is done. The final kind of t-test that we can run is called the paired t-test, right here. Paired t-test is used when you're looking at the same group but under separate conditions. Say you were looking at how well you can treat cancer using drug A versus drug B. So you take the same person, first put him on drug A, see the results, take the same person, put him on drug B, see the results, and then compare. So it is the same group under different conditions. That is when you use the paired t-test. Or it could also be time dependence. So conditions could also be time. Say you put the person on drug A and looked at him after 3 hours as compared to 10 hours, or 3 days compared to 10 days, 3 months compared to 10 months. It is the same person or the same group. You are just comparing the same group under different conditions, either time points or under different conditions like drugs or whatever else you can figure out. That is when you use the paired t-test. This one I am leaving for you guys to figure out how to work with. Very same to independent and one sample t-tests. Okay, so we are done with t-tests. Any questions anyone has? Okay, so the next type of test is does anyone want to ask anything?
Sir, could you explain Cohen's D?
Yes, Cohen's D. So say you were actually so every one of the one sample t-test as well as the independent t-test both have given us Cohen's D. Cohen's D is essentially the practical implication of your result. As I said, say you were looking at marks in a particular exam, one person got 95, the other got 98, or one person got a 40 and another got a 32. So significantly they are different. Maybe if you actually figured out how different they are, you found that they are actually significantly different. The p-value is less than 0.05. But the question is, does it practically make sense that the values are actually different to each other? Do you actually care on a practical sense? Like, do you actually care if someone is getting a 95 compared to a 98? You probably don't. So that is where the Cohen's d comes into the picture. If the Cohen's d is more than 0.8, it shows that there is a practical difference between the two values. It is not just on paper that there is a difference, but actually practically you have to keep in mind that there is a difference between the two. Normally Cohen's d is not used much in scientific approaches. You actually look at it like in research. I have not actually seen much of use of Cohen's d. Mostly people just report the p-value, but this is something that you keep in mind. So practical effect size of the difference between the two populations, you look at Cohen's d. 0, it is greater than 0.8, even 0.5, there is actually a practical difference. Less than 0.2, you actually don't care. There is not much practical difference, even if the on paper the p-value is different. Is that fine?
Yes, sir, understood.
Okay. So we were dealing with t-tests and figuring out if 8 cylinder is more than 6 cylinder, if 6 cylinder is more than the population mean. So you're dealing with two means at max. So use the t-test. What if you actually have to use more than two? Then we have a all, one test to solve everything. You don't have 2, 3, 4, 5. You only have one test to deal with more than two means, which is called the ANOVA. So two, how many groups? There are more than two. You use the ANOVA test. So how do we use the ANOVA test? You can go over. So ANOVA is very easy. You just again make one data set with all the groups that you want to compare. So say we compared 8 and 6 and the population. What if we want to compare the 4 cylinder group as well as compared to the 8 and the 6 cylinder groups? So the three different groups we are now comparing. So in that case, first thing you do is the same thing that we did previously. You make one data set containing the data that you want to compare, the 4, 6 and 8 cylinder cars you want to compare. So you make one data set. So already empty cars has 4, 6 and 8 only. So you're not making any, like you're not filtering for anything, and you put the cylinder as factor. The same thing that we have been doing. And then you run the ANOVA. The ANOVA runs with the function AOV, followed by the same idea as previously. You have a formula. The formula puts in what you want to compare and the groups. So you want to compare this HP, and the groups that you compare between are the cylinders 4, 6 and 8. Again, it only takes as factors, that is why we have put cylinders as factors, and the data is obviously my empty cars that we just made. And here, instead of just displaying ANOVA test, you have to do summary ANOVA test. So everyone please do it. So when you run it, you get this enormous table with so many values. The one you care for is again this PR value, which is essentially the p value for ANOVA test, which is you look at if it is less than 0.05, And if you remember, if it is p-value is less than 0.05, then you have 1 star significance. If it is less than 0.01, then you have 2 star significance. If it's less than 0.005, then you have 3 star. So obviously this value is less than 0.005, so you have a 3 star significance in the ANOVA test, which shows that the at least two groups between the three are different from each other. Everyone with me so far?
Sir, can you explain the output once again?
Yeah, so the output is pretty complicated. We only look at this value, the PR greater than F, which is the P value for the ANOVA. So as you remember, P value less than 0.05 is significant and has a 1 star associated. So here it is written, see, it is less than 0.05, then it is significant and has 1 star, less than 0.01, 2 stars, less than 0.001, 3 stars. So here you look at the p-value, you see that it is 1.32 into 10 to the power minus 8, which is obviously less than 0.001. So you have a 3 star significance to your data, which means that the in the three groups that you compared, 4, 6 and 8 cylinders, at least two are very different from each other. So when you compare, actually when you're comparing means you don't compare all the three together, or if you have more than three, you don't compare all of them together. You compare between 4 and 6, then 6 and 8, and 8 and 4, like this. So you compare in pairs only. So this test shows that at least two groups are significantly different from each other. Is that fine?
Yes, sir, thank you.
Okay. So now the question is actually which groups are different. So as I said, ANOVA gives you the result that yes, out of the 3 or 8 or 50 groups that you compared, two are different. But which two? You don't know from ANOVA. So you do another test which is known as a post hoc test. And here we are doing the two keys post hoc test. There are three different ones. Most commonly used is two keys, and running it is very easy. You use the function 2key hsd and then ANOVA test, which is the result from this ANOVA here, and it actually gives you compares the two groups 6 and 4 and gives you a p-value. So you compare which p-value is less than 0.05, and that gives you the idea that yes, these are the two that are different from each other. But here as you can see, 6 and 4 cylinders are not actually very different. They are not, the p-value is not less than 0.05. It is 0.09. So the HP between 6 and 4 cylinders is not different, which ANOVA didn't tell us. But between 8 and 4 cylinders and 8 and 6 cylinders, you see that it is less than 0.001 even. So 8 and 4 and 8 are 6, these two groups are actually different from each other, which you get from the two keys post hoc test. So so 6 and 4, these two HPs are not different. 8 and 4 and 8 and 6 are different from each other. Is that fine? Any questions, anyone? Run this once and let me know. Everyone okay with this? Yes, no, kichada bolo.
Yes, sir.
Okay. So we have two-way ANOVA, two other things left, but I think I will leave it for the next class because it will be a lot to digest anymore, I feel. ठीक है, so this is where we end today. Today is the 7th class. कल के 8th class से परे we will actually have finished the first two modules, and then I will finally give you your assignment for the first two modules will be together, which I figured out it will be best if I do the two modules together because they are pretty related and you will have better questions to answer that way. The other thing that I wanted to tell you is that I am traveling, that I am abroad, so not around, so I might not be able to answer emails very frequently or answer them at odd times. So just wait. I will answer emails and everything that you put on or WhatsApp messages, but they might be at an odd time or a bit late. So that is all for today. I will quickly take your attendance. Does anyone have any questions regarding what we have talked today or any day before? Then you can please ask now. Okay, since no one is asking anything, I believe everything is completely fine. Uh, then thank you everyone for joining today. We will meet you tomorrow.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.